Hi guys, my friends and I will be presenting about Huffman Coding. Without further ado, let's start. Huffman Coding, or also known as Huffman encoding, is an algorithm used for data compression. It was developed by David Albert Huffman. He made a research on it in 1952 called A Method for the Construction of Minimum Redundancy Codes. Generally, this algorithm works by assigning characters to a variable number of bits or codes depending on how frequent the characters in the given text. Smallest code will be assigned to the most frequent character, while the largest code will be assigned to the least frequent character. Now, let's get into more details about Huffman coding, shall we?
So now we are going to talk about the science and theory behind the Huffman coding. Huffman coding is a lossless compression where it compresses the data without any loss occurs. The encoding consists of two processes, the statistical and the encoding itself. During the statistical, each character in the plain text is counted. This includes white space characters as well. Then, they will arrange according to their frequencies in descending order, forming a table. From the table, during the encoding, which is the second part, two of the characters with the lowest frequency will form a temporary node with two branches. The second lowest is the left branch, while the lowest will be the right branch. The temporary node will then calculate the sum of the two branches and will be put back into the table while keeping the descending order. These previous steps were repeated until there were only one node left, which is the root of the Huffman tree. Finally, the message is encoded with each character is translated to their encoded path from the root.
Let's continue to the concept of the Huffman coding. So as you can see in this slide, we take an example. This is a short example to understand the concept. So we take the she cells at the seashore. So first of all, we need to take all of these letters and make it into and put it into a table and count how many of the letters. So for example, like this big S, the capital S. So there's one. So and then put one, and then just do this for every letters that you can see, including space and the dot. So and then after we had count them and put them into the table, so then we are going to add two lowest the characters and create a node with the node frequency having the sum of the frequency of each characters. So like you can see, we take these two, which is the lowest one, like the O and the capital S. We sum it up and become a 2, and it will become the first node, which is 2. And then we will take the previous step repeatedly, like this one, 1 and 1. So this is the lowest. We added sum them up, and it will become the second node, which is 2. Okay, and then what if we deal with the node instead of characters, because the lowest one is 2, the first node. It's still the same. We do the same steps, which is we just sum them with these letters, like node 1 plus with the letter T, and we got this third node. Okay, and then just repeat the steps and we will have this 3. Okay, so like this one, this S, O, R dot, and every letters. So as you can see here, if we go up here, which is the red one, which is it will represent a 0, and if we go down, which is the green one, it will represent a 1. Okay, so then we will make the encoder table, which is for the S, small s, from the table we can see this is the small s, so the green is 1, so 1 1, so this is the S. Hence we will get this S11. For E, like for example E, we got here, so 0 0 0. So we got, and just do for every single letters. So then with the message, we got she cells. So from the capital S, we just write it back. Oh sorry. So 0 1 0 0 1 1 0 1. So just put 0 1 1 0 1, and then H 1 0 1, and just repeat the step until you get this binary code. So how to decode this code? Okay, maybe you have the code, binary code, but you need to decode it into a sentence. It's easy. just refer to the Huffman tree again. So for example, we got this binary code. So let's start with 01101. So for example, from the root, so the first number is 0, so 0, and then 11, 11, 01, 01. So we got the big letter S. So and then we stop here. So we got the capital S, and then we start again. 1, so 1, for example 115, and then 0, 0. 1, 1, 0, 0, 1. So we got H. So and then we got H, and then we just repeat the steps until we got this full sentence, which is she sells at the she's.
Okay, I will continue with the video presentation where I explain about the example of Huffman Coding. Okay, the example was taken in a text from IOM website as shown in the figure. Okay, the text is the description of the IOM logo, and we use the text as example of Huffman Coding. Okay, as the previous example, the first step of Huffman Coding is to count the number of characters and arrange them in descending order. As shown in the table, space is at the top of the table because it is most counted characters in the plain text, which is 29 times counted. On the other hand, the character Y, B, W, capital A, open bracket, close bracket, capital W, and dot are at the bottom of the table because they have the lowest counted characters in the plain text, which are only ones. Okay, next, we make a tree that will further explain by my friend Shahamil. Okay, after we make the tree, we can list the encoded message in a table as shown here. As shown in the table, space is coded as 010 in binary form. The encoded message is following the tree that we made just now. Okay, lastly, we got the encoded message in binary form as follows, where the highlighted binary code represents the letter capital T in the plain text. Thus, to decode the binary code here, we reverse the encoded messages table before this and compare the letter and the binary coded.
So now, as Alif showed in the slide before, the character is already arranged in decreasing order. So the top frequency will be space with the highest frequency of 39, and the bottom one is the lowest frequency as low as it goes, like frequency 1 over here. Okay, the low frequency one. Okay, what we're going to do is we're going to take the pair of the lowest frequency. For example, we have here is the close parenthesis and dot share the same frequency of 1. So what we're going to do is we're going to add up the frequency and we come the frequency 2 over here. So we're going to make the number 2 as the node. Okay, so now the frequency is become 2. We need to rearrange back in decreasing order manner, because now this is the table is not in decreasing order because the 2 is not the 2 is obviously is bigger than 1, the upper frequency over here. Okay, this is 1, this is 2, so we need to rearrange back. How do we need to rearrange? Okay, the node 2, the total frequency inside the node is 2, so we need to put the node below the higher frequency. For example, over here the higher frequency available now is 3 because 3 is higher than 2. Okay, so we need to put this node we need to put the node here, between the comma and the capital T. Okay, I gotta speed up the process for a bit. Okay, now as you can see, the node 2 is between comma and T, capital T, because the comma has the higher frequency than, which is 3, and T is the same frequency. So what we're going to do next is we already rearrange it in decreasing order manner, so we need to continue the pattern. Okay, we take the two lowest frequency, we add up together and become one node. Okay, it has the same frequency of 2. So as usual, we need to put it below the higher frequency. In this case, the higher frequency than 2 is 3, so we need to put it below 3. So the position of this new node will be between the previous node and the tree. Okay, so the process will be going on and until we get the single root of the tree. Okay, so for this process, I'm going to do a time-lapse version, so enjoy the show. Okay, we are back. So now, as you can see, the time-lapse process, that's how the Huffman tree encoding are constructed. But during the process of the work, I make a mistake somewhere. It makes the tree that is constructed by the computer is different than mine. Yeah, the human mistake for sure, because the more character there is to be encoded, the more likely that human mistake will be happen, right? Okay, therefore for sure the longer time it consumes to make the tree, even the computer takes time to make the tree. Okay, so the final product of the tree should be look like this, as shown in the example in the slide. It should be look like this. Okay, from the tree you can see it's noted that the red will be the zeros and the green will be 1. Okay, for example, if we want to encode the dot over there, so we need to see, okay, the flow. This is 0, right? The red means 0, the green means 1. Okay, 0 0 0 1 0 0 0 0. Okay, the encode for the dot should be 0 0 0 1 0 0 0 0. Okay, let's check the table that has been constructed. 0 0 0 1 0 0 0 0. Okay, it is true. So that's how a character be encoded from the Huffman tree constructed. Okay, how about we take another example? Okay, how about we take the lowercase p over here. Okay, the lowercase p should be 0 1 1 0 1 1. Okay, p should be encoded 0 1 1 0 1 1. Okay, let's check. 0 1 1 0 1 1. Okay, that is true. So that's how a character be encoded in Huffman tree. Okay,
about the limitation of Huffman coding. Firstly, Huffman coding is lower compression ratio compared to other lossy encoding techniques. This makes the Huffman coding only suitable for encoding text and program files. It is unsuitable for encoding digital images. Next, it is not optimal for all cases, such as when the symbol by symbol restriction is dropped or when the probability mass functions are unknown. Next, the Huffman coding are considerably slower than other techniques. This is due to using the 2+1 for the building statistical model and encoding. This makes it is a relatively slower process. Next, the decoding software may have difficulty to detect if the encoded data is corrupted or not. Different length of binary codes making the decoding software harder to detect whether the encoded data is corrupted or not. This may result in an incorrect decoding and subsequently a wrong output.